All right, so in the last lecture, we derived the conservation of momentum equations. And now we're going to think about the concept of viscosity and the Navier-Stokes equations. First, let me write down what the equation of motion is for the, not the equation of motion, but the conservation of momentum equation. I guess they're the same. D by dt, the time rate of change of the momentum, rho v, per unit volume, plus the divergence of the momentum flux, which is rho v is equal to F, where F is the applied forces. And in this case, I've put it so that the pressure gradient force is in F. Okay, so if you imagine looking at the ocean, there's a very large range of length scales at which there's motions, from very tiny turbulent eddies where the crest of a wave is breaking on a beach, which is at millimeter scale and smaller, all the way up to the thermohaline circulation, which spans the global ocean, so tens of thousands of kilometers, and spans the full depth of the ocean. And that's a very large range of length scales, and it means that there's no way we can describe the full ocean circulation in all its details. All we can try to hope to do are two extremes, I guess. One, take a very small patch of the ocean and describe what's happening at small scales in that very tiny little patch. So if we're going to do motions on centimeter scales, you could imagine having a cube of water on a supercomputer. That would be, you would simulate that at a few cubic meters, and then you can resolve all the way down to the centimeter scale on a very powerful computer. But if you're trying to describe the global ocean circulation, then there's no hope to resolve things all the way down to centimeter scales. The best you can do is simulate down to some finite length scale, maybe 100 kilometers or so, for a 1 degree resolution ocean model. And even that is taxing if we're trying to do long climate simulations for long times. So what we have to do is somehow derive a system of equations that will be applicable to only the large scales, so ignoring the small scales, or maybe not ignoring them, but figuring out what their effects might be on the large scales. This equation, the conservation of momentum, involves these nonlinearity terms, right? The VV term here, which is the advection of momentum by the currents themselves, right? So it goes like a quadratic in the momentum term, in the velocity term. And so what we're going to do to think about this separation between large and small scales is we're going to imagine that we can separate the flow field, the V, into two parts, V large scale plus V small scales. And so far I haven't done anything except redefine what V was into two functions instead of one, so no advance. But what I'm going to assume now is that V varies only on large scales, whereas Vs varies only on small scales. So somehow assuming that we can separate the flow into two parts, large scale and small scales. And the way I formalize that is by assuming that on small scales, the large scale motion is a constant. So if I define some averaging operator, this averaging here, and I put the large scales in there, then this averages, so maybe it takes an average over every 100 kilometer patch. And everything at 100 kilometer resolution, or whatever the separation is, this VL doesn't vary, so it's a constant. And so the average of a constant is just the constant itself. So it's constant on small scales, but not on large scales. So VL will vary, but on larger scales than what my averaging operator is. On the other hand, Vs has no large scale variation. So if I average Vs, the small scale flow, then the assumption is that that just averages to zero. So everything that varies on scales of the averaging and larger is VL, and everything else averages to zero. Right, so I've done this decomposition. And what I'm going to do now is I'm going to substitute this decomposition into the momentum conservation equation, and then I'm going to average the equation and see what I get. Right, so if I sub in, I'll get d by dt of rho v plus v large scale, small scales, plus the divergence of the flux operator, so that'll be rho, not the flux operator, the flux tensor, the momentum flux, or momentum current tensor. V large scale plus V small scale, V large scale plus V small scale is equal to F large scale plus F small scales. And now this part here I can multiply it out, right? So this part will become V large plus 2 V large Vs plus Vs. And that's it. All right, and now I'm ready. I'm going to average out the equation, right? So this is a spatial average, this angle bracket, so I can take it inside the derivative. And for simplicity, I'm going to assume that rho is a constant. So assume rho is a constant. And we're going to assume it's a constant for the purpose of deriving equations for the momentum equation. We could, in principle, retain large-scale variations of rho in the continuity equation, right? So, but for here, inside the momentum, we're going to assume that the variations of rho, to the extent that they affect the momentum of the water, is a negligible variation. So it's a good approximation that we can approximate it by a constant. Now if I apply the averaging operator, the angle, I could take it inside, and if I average VL, I'll just get back VL, and if I average VS, I get back VS. So I guess an aside, for those of you who haven't thought about these things, is if I average two functions, f plus g, or more general, average some alpha, some scalar times f, which is a function, plus beta times g, right? That is the same thing as alpha times f plus beta times g. So this is called a linearity property. So averaging is a linear operation. All right, so you can verify this if you just take the regular average, where you just sum and divide by the total number of observations. You can check that averaging satisfies the property of linearity. So I'm going to use that because when I take the average inside here, rho is assumed to a constant, so I can take it out of the averaging, and the average of VL plus VS is just the average of VL plus the average of VS. And the average of VL is just VL, and the average of Vs is 0. So this term becomes d by dt rho VL plus. And here also I'm going to take the averaging, and I'm going to take the averaging inside the divergence operator. So that's not so correct. In fact, what I need to do, because the averaging is an averaging in space, and the divergence here is a spatial derivative term. And so what I need to do is average the whole thing and then integrate by parts to get the divergence of the average plus some boundary terms. I'm going to skip over that because it's a fast and loose lecture. I'm just going to assume that I can take the averaging operator inside the divergence. Maybe I can come up with a homework where you guys can show that that's okay. So I'll take the averaging inside, and so I'll end up with divergence of rho, and now I'll get the averaging of VL with respect and VL plus 2 times the averaging of VL VS plus the averaging of VS VS is equal to, and then I have the averaging of the large scale forcing, which again, since F is on large scale, this will just be the large scale forcing. And the averaging of the small scale forcing will go to 0. So the forcing at small scales seems to be irrelevant in the context of this equation. Okay, next thing is I'll go up back to here, and I will point out that the averaging of VL and VL, well, both of these are constants on the scale of the averaging, so they can both just return back VL. So the averaging of VL is just the product of the large scale velocities. The averaging of VL and VS, this term here, well, VL is a constant with respect to the averaging, so I could take it out of the averaging operator, and then the average of VS is just 0. So this becomes VL times the averaging of VS, and this one is just 0, so the whole thing is 0. So this term vanishes, and then I have the averaging of VS. And And this one, you might think, well, the average of Vs is 0, so we can throw it out, but that's not the case here because we have the product of the two. And if there are correlations, then they may not average to 0, right? So this term, we can't throw it out. We have to keep this one. This one is not necessarily equal to 0, and so we're not free to throw it out. And then if I put that substitution, the equation become d by dt of rho VL, the large scale momentum, plus the divergence of rho VL plus the divergence of this one vanished, this one I have here, and left with that one, of rho VS equals F at large scales. And this equation looks a lot like the original equation we had, right? Except now V is replaced with VL, right, in these terms. This is the original equation. This was there, except it was the full F. But we have this new term. So this one here, this is a new term. And it involves the small scale flow and its influence on the large scale flow, right? So what are we going to do, right? It seems that there's no way around knowing the motion of the fluid at all scales, right? This term forces the large scale. So in order to solve the large scales, we need to know the small scales. And so we would need to derive a second equation for the small scales. And so what people do in practice is we're going to assume that somehow we can write this correlation of the small scales in terms of the large scale. So that's a hypothesis, which may or may not be true, but that's what we're going to assume. And so what we're going to do is we're going to assume that the current for the small scales, which is defined as rho VS. So the momentum current at large scales due to the small scales, we're going to assume that this can be written in terms of the large scales, can be expressed in terms of VL. So that's an assumption, right? And to the extent that this assumption is good, we will get a good model for the ocean circulation. If it's bad, we'll get a poor model. So what would be a good way to parameterize this thing, this current of momentum due to correlations between the small scale eddies? So maybe a picture could be useful. Suppose that we have the large scale flow, right? This is like meant to be the velocity, something like this. Right, so this is there's a shear, right? This is the large scale flow, and somehow there's a shear. So in other words, the velocity is fast up here, and it decreases to 0, and then it changes direction, and it started increasing again, but in the opposite direction. So we're assuming that there's a large scale shear, large scale shear. And then we imagine that there's some small scale motions superimposed on this, right? Remember, the full flow is VL plus VS. And so these small scale eddies are swirling around. Right, and they average out to 0 on, maybe they go in different directions in different parts of the flow. Right, there's these eddies. So these eddies are swirling around, and you can imagine that when a fluid parcel moves upwards, if it starts from further down, let's assume this is the south, that's the north, it's going to carry with it momentum, large scale momentum, which is a little bit less than it is up here. So it seems to be fluxing momentum, smaller momentum northwards and faster or bigger momentum southwards. So every time you churn things out, it seems that what's going to happen is that the momentum, the large scale momentum, is going to get mixed, and over time this profile will start changing, right? Or there will be a transport of momentum, a current, going from the high momentum to the low momentum, right? So what we're going to say is we're going to assume that J assuming is some proportional some constant mu times the gradient of the large scale velocity. And more than that, it goes from the high momentum to the low momentum, so there's going to be a negative. So this parameterization we've seen before, right? That's the Fick's law, so that's the one that we use for diffusive flux. So we're assuming that momentum diffuses the same way that salt or temperature diffuses. And the only difference is that here, the diffusion is not due to a molecular motion, it's due to the eddies. The same way we did in that 1D balance for temperature and oxygen and radiocarbon. So, but now we're doing it for momentum. So that's the assumption. So this is our model. Put it in the box. And we're going to substitute that into the equation to see what we get. All right, so the beauty, or the whole point, is that this term here now is expressed in terms of the large scale. So then the equations become d by dt, rho v, the momentum density again, plus div dot rho VL, plus the divergence of minus mu grad VL is equal to FL. All right, so mu here, it can be a function of space, depending on how we parameterize it, then we have to leave it inside the divergence. Or for simplicity, let's assume that mu is a constant. So if we assume this is a constant, then we get if mu is assumed constant. But having a function of space poses no real difficulty. It's just for simplicity here to make the equation neater. D by dt, rho v, plus div dot, rho v L VL, plus, and then the minus mu, and then I get the divergence of the gradient of VL equals F. All right, so this divergence of the gradient, let's see, I'll show you what this is in terms of Cartesian. We've done it in the 1D balance, right? We have the divergence of the vertical advection and the vertical diffusion. And remember what we got was a second derivative term, right? Partial a kappa d2 dz squared, right? In the model in the Mach model. And it'll be the same thing here, except now this is in 3 dimensions. So if I write it out here, so divergence of the gradient of V is the same thing as d by dx plus d by dy plus, I'm doing it in Cartesian for simplicity, plus d by dz times the gradient. So I'll have du dx, du dy, du dz, or maybe I should put them horizontally. Du dx, du dy, du dz, dv dx, dv dy, dv dz, and dw dx, dw dy, dw dz. So the first row is the gradient of the x component of the momentum. The second row is the gradient of the y component of the momentum. And the third row is the gradient of the z component of the momentum. And now if I take the divergence of each of those terms, what I get is d2u dx squared plus d2u dy squared plus d2u dz squared. That becomes the first component of this expression. The second component is dv dx squared plus d2v dy squared plus d2v dz squared. And the last component, I guess I have to erase, is d2w dx squared plus d2w dy squared plus d2w dz squared. All right, so this is what the divergence of the gradient is. And this expression here, this sum of second derivatives, that has a name, this operator, and we call it the Laplacian. So, and we usually express it as del squared, or sometimes the upside down triangle, and in Cartesian it's d2 dx squared plus d2 dy squared plus d2 dz squared. So this is called the Laplacian operator. It's called Laplacian operator. All right, so our extra term, our parameterized term for the small scale and the large scales has is expressed as a Laplacian applied to the large scale velocity. All right, so then the equation which I just erased, I can now rewrite it using this Laplacian notation. So this becomes equation, the momentum equation, becomes d rho v large scale dt plus div dot rho v large scale v large scales minus mu Laplacian of v large scale. So this is the new term, right? The new term that parameterizes j small scale defined as rho vs vs as minus mu del squared v large scales. And then on the right hand side we have the forces. So these new equations, these are called the Navier-Stokes equations. So this is the Navier-Stokes equations, where we've added this extra term to the original momentum conservation that has a del square term, and this turns out to be a damping term. So and a damping term of the small scales preferentially. So this is a kind of a diffusive, or is viscosity, and it mixes momentum. So that the viscosity will transport momentum from regions of high momentum to regions of low momentum, and it kind of smooths it out. And this viscous term will push the momentum out, even it out uniformly, until it reaches the boundary. And at the boundary, then there's going to be a solid wall, and something else will have to happen. And what happens is that the momentum will get fluxed into the boundary, or will get dissipated, will be transferred to the large, transferred to the boundary. So there'll be some rubbing against the boundaries. And so with that bit where I took the averaging inside the divergence and I neglected what happens on the edges, that involves a treatment of how we treat the boundary conditions. Okay, so let's demonstrate that this term does indeed act like a removal of small scale properties of VL. So that means that as the flow evolves, the turbulence may try to take the large scale and stretch it out and form small scales, but this term here will be able to remove those continuously, making sure that the flow remains always a large scale flow. So if this viscosity is large enough, then the flow, which is of some complicated nonlinear equation, will never be able to produce any small scale. So as it starts to shear out and stretch the flow, then it's going to produce some small scales, but these will damp them out, is the claim. So let me rewrite the equation a little bit nicer here, just so we put in the usual term. This term, usually the minus, we bring it on the other side of the equation, like this, plus f. I should have increased the f. So we just, what used to be minus mu, I brought on the other side, now is a plus. Okay, so we want to show that if VL has small scales, then this will act to remove them, right? So the way to think about this is to imagine that we have, let's just take one component of V, the first one, U, and suppose that U has some wave, a sinusoidal wave. So U is equal to sine k times x. Let's pretend it just goes in the x direction. And k here, that's, so right, this looks like an oscillation, right? And k, we can think of it as k is equal to 2 pi over lambda, where lambda is the wavelength. So lambda would be this length. and lambda as units of length, so that k has units of inverse length, so that k times x is dimensionless, so that we can take the sign of it. Okay, so if I have u is this way, then if I apply the Laplacian to this thing, remember the Laplacian of u is going to be d2u dx squared plus d2u dy squared plus d2u dz squared. Well, d by dy of this is 0, so that does nothing. D by dz of this is 0, so this does nothing. But d by dx of sine is going to be a minus k cosine. Or sorry, no, it's going to be plus. It'll be a plus cosine kx for the first time. And then the second derivative will pull out a k again with a minus. And so what I'll get is minus k sine, and I get back to the sine when I take two derivatives of kx. And each time I popped out a k, so I get a k squared, right? So the second derivative of this will give me minus k squared, and I get back the original function. Okay, so now let's imagine what happens. So notice there's a minus sign, right? This is positive, and there's a minus over here, so the whole thing is negative. Right? K squared is positive, minus k squared is definitely negative. And so what's going to happen to the wave? Well, it'll get damped, right, at a rate. So I get back the same flow, and there's going to be a minus, so the d by dt, right? So if I neglect the other term for a second, that means that du dt, right, I have a row. Let's forget about this term for now, equals minus k squared u, right? I get back u. Sine kx was the original u. And what we see is that u will get damped, right? This is like, if I can neglect these terms here, if I can ignore them, the time rate of change of u will be negative, right? It'll be going in the opposite direction, like k squared. And so it'll tend to damp out the flow, the u, the variations in u. And it'll damp out the bigger the k is, of course, the faster the damping will be, right? It's proportional to k squared. And so what is a big K? Well, a big K is a small lambda, right? So it's a small wavelength. So if I have another wave that looks like this, right? This one will damp out much faster than this one, because this one, the K is much smaller, right? The K goes like the inverse wavelength. So this operator, this Laplacian operator, has the virtue of damping out small scales much faster than large scales. So in fact, the very large scale flow, right, is going to get only very weakly damped. But as these terms start generating smaller scales, right, as we approach the scale of the averaging operator, a little bit longer, but right, we have that angle bracket. So that averages everything that's smaller than a certain scale. But if we're coming in from the large scales and we're forming smaller and smaller scales, as we approach that scale of the averaging operator, this Laplacian will tend to damp things out, and the variations in the flow is going to go to 0 by the time we reach the scale of the averaging operator, keeping the whole system of equation consistent. Okay, so this is a lecture on viscosity.